Welcome to this next video in which we are discussing polynomial rings. Okay, so we have now succeeded in defining an addition law on our set of polynomials with coefficients in our commutative ring R. Okay, and this addition law we have now verified obeys all of the axioms in a abelian group, so it's all looking good. What we now need to do is define a multiplication law on our set of polynomials. Now, multiplication is slightly more difficult to define than addition, and before we actually go on to define multiplication, what I want to point out to you is a really important fact that's going to help us in our understanding of multiplication. Okay, and this is the fact that you can decompose any polynomial now in our set of polynomials down into the addition of a whole bunch of monomials. Okay, now let me just remind you of something. Okay, so far, the polynomials that we've had in our set have been these very abstract structures. They've been the sum over I, and I'll drop the I is equal to 0 to infinity now. I'll just write the sum over I, okay, of these terms, ai, xi, like so. Okay, they've just been these abstract structures, these abstract symbols where you've had coefficients in front of these powers of x. Okay, and remember, the plus symbols in between the terms, those were just symbols. They didn't mean anything. It was just, you know, creating a symbol. This was just a symbol where the coefficients in front of the powers of x were just elements of our commutative ring R, and you had only a finite number of the coefficients not being the 0 element of the ring. Okay, now what we're going to do is change that point of view, okay, because we can now view those plus symbols as actually being plus in the ring of polynomials now, because we've defined what it means to add any two polynomials together. So what we can actually say is this polynomial here, it's actually the sum of loads of monomials. Okay, so in our ring of polynomials, the monomials are all elements of that ring. Okay, so what do I mean by a monomial? I mean a polynomial where you've only got one non-zero coefficient within the ring, okay, and that's in front of some power of x. So something just of the form, let's say, how should I denote this? I will put I, xi, okay, where I is just some fixed value, some fixed non-negative whole number. Okay, so this is a monomial here, and all of these are polynomials. They're just the special polynomials where the coefficients in front of all the other powers of x are just all 0. Okay, so these are in our set, and what we can now do is split any arbitrary polynomial over here which has loads of terms. I can split it down just into the sum of monomials, where the way that you will add monomials is just the way that I've defined addition of polynomials now. It's component-wise. Okay, so I can now view this polynomial as actually being a real sum. Okay, and I want you to understand the difference, because I'm going to write out the exact same thing here. I'm just going to write out the sum over I, ai, xi, but it means a different thing now. Here, what this sum meant is just create this symbol where you put plus in between all of the terms. It was just a symbol. It didn't actually mean addition in terms of any algebraic structure. Now what I'm saying is this actually does mean addition in terms of an algebraic structure now. It means addition that we've just defined in our ring of polynomials where we are adding the monomials together. So this can be decomposed into a sum of monomials where those monomials will be the powers of x with the relevant coefficients from the ring in front of them, and we're just going to add those together in our ring of polynomials with the addition law that we've now defined. Okay, so there's a subtle change in the philosophy of what we've got here. Okay, this was just a symbol, and fundamentally the ring of polynomials is still just this set of symbols. But now what I can do is I can think about decomposing a polynomial in my ring of polynomials down into a sum of monomials from the ring of polynomials, where the sum is carried out in the ring of polynomials with the addition law that I have just defined. Okay, and this is actually going to be helpful for us in understanding multiplication of polynomials. Okay, so understand how those two things are different, how the philosophy behind them is different. This actually does mean addition, whereas this was just to create this symbol with the pluses in between the terms. Okay, so what I now want to do then is define multiplication, and we're going to use this fact that we can decompose any polynomial just into the sum of monomials, where the sum, the addition, is carried out with the addition law that we've now defined. Okay, and the way that I'm going to start by defining multiplication is I'm going to define how to multiply two monomials together. So if you pick one monomial from the ring of polynomials and you pick another monomial from the ring of polynomials, how do you multiply those two together? And then what we'll move on to is we'll use this fact that any polynomial can be decomposed into a sum of monomials to then define how we will multiply any two polynomials together. Okay, right. So the way I'm going to define monomial multiplication then, so if I've got one monomial here, ai, xi, where I is some non-negative integer, and I want to multiply it now with another monomial, so here's one monomial, and I want to multiply it with another monomial, bj, xj, where again j is some non-negative integer. Okay, how am I going to define this then? Okay, what's the common sense way? What you're going to do is you're going to multiply these two coefficients, the ai and the bj, together in the ring. So this is going to equal ai times bj, and that multiplication will be done in our original commutative ring, capital R. So I'll just make a note that this is an element of capital R, because remember, the ring will be closed under multiplication, so this will be some other element of the ring, capital R. And then you're going to have that as the coefficient for some power of x. And what's our new power of x going to be? Well, we're just going to add together the two powers. Okay, so you'll just add I and j together in the normal way that non-negative integers are added together. Okay, so that's the way I'm going to define the multiplication of two monomials. And indeed, it does give me another monomial which will be in my ring of polynomials. Okay, right. So what I'm now going to do is I claim that now we've got this, there is only one way that multiplication of polynomials can possibly work, because I want this structure that I'm overall creating here to be a ring. Okay, and rings have to obey distributivity. So what I've already said is that any polynomial can be written as the sum of monomials, where the monomials are being added together in with the addition law on my ring of polynomials now. Okay, so what I can do is, if I've got two polynomials here and I want to know what the multiplication of them together is, so here's one polynomial here, and here's another polynomial here, so the sum over, let's say, j, bj, xj here, so here are two polynomials now, so they've got lots of terms potentially that are non-zero, not just one, as was the case in the monomials there. Okay, well, what I can now do is acknowledge the fact that I've got up here. I can express this as a sum of monomials. So now, instead of thinking of this just as a symbol, instead of thinking it in the red way here, think in terms of it in the turquoise way here, and do the same for this one. Okay, so both of these are just great big sums of monomials, where the sum is carried out in the ring of polynomials addition law. Now what I can do is say, okay, if I want my multiplication law to obey distributivity, then there's only one way this can work. Otherwise, the multiplication law won't obey distributivity. I've defined what it means to multiply any two monomials together. Okay, if I want my multiplication law to obey distributivity, if it's got a hope at all of obeying distributivity, this one multiplied by this one is set now. It's set in stone by these two things. Okay, all I'm going to have to do is take every single term from here, okay, all the monomials from here added together. I'm going to have to go through each monomial one by one and multiply it with every single monomial over here. Okay, and then add together all of the final things. That's just applying distributivity. Okay, so if I want polynomial multiplication to have a hope at all of obeying distributivity, that's the only way I can do this. Okay, these two things together have set in stone what this has to be if it's going to obey distributivity, or if it's got a hope at all of obeying distributivity. Okay, so what this means overall is that I now have to go over the sum over I, the sum over j, and I have to sum together all of the monomials multiplied together. So I'm going to need ai bj, like so, and I'm going to have x I plus j, and you're just going to go over all I and over all j and sum all of these monomials together with the addition law that you've got in the ring of polynomials. So I hope you understand why that is true. It's because I've decomposed this into a great big sum of monomials. Writing this explicitly out, I could write it as a0 plus a1x plus all the way up to anxn, where n is the highest monomial power that has a non-zero coefficient. And understand that these additions here are additions in the ring of polynomials now. We're adding all of these monomials together in the ring of polynomials to get this polynomial. Okay, this is not addition just as a symbol now, as it was in the red interpretation up here, as it was originally, but now I've decomposed it into its monomial sum. Okay, similarly, I can do the same for this one here, so I can have b0 plus b1x plus all the way up to bm xm, where m is the degree of this polynomial. Okay, and again, these sums will not be according to philosophy 1, but according to philosophy 2 here, the new philosophy. Okay, so it will be decomposing into a monomial sum. And now, if the multiplication is to obey distributivity at all, then this has to just become this one times this one plus this one times this one plus this one all the way up to times this one, and then you have to go through this one times this one times this one, all the way up to this one times this one, and then onwards all the way up to this one times this one times this one, and this one all the way up to times this one. Okay, that has to be the case if we want it to obey distributivity. Okay, and if we don't define it like that, it won't obey distributivity. It doesn't have a hope of obeying distributivity. So that's all it can possibly be defined as now, once we've defined monomial multiplication, and once we've said now that any polynomial can be decomposed into a sum of monomials. Okay, so it does then just become the sum over I, the sum over j of all of these monomials multiplied together like so. Okay, so that's going to become our answer here. Now, what you would have to do in order to get an explicit formula for your final polynomial is you then have to add together all of these monomials, because understand that these two sums here, these still mean sums in terms of the addition law on the ring of polynomials. You are adding together all these monomials in the ring of polynomials, and then you'll get some final polynomial. Okay, so you can get an explicit formula for the final polynomial in this sort of philosophy here, where it is just a symbol. Okay, and I think I will now do that. However, when you're trying to prove facts about polynomial multiplication, it is better to think of it in terms of this way. It's better to write these two polynomials multiplied together in this form, i.e. as the sum of all these monomials, where the sum is carried out in the ring of polynomials, i.e. according to turquoise philosophy, and I should have turquoise at some point in this. I might box it in turquoise, okay, because turquoise philosophy is really important here. Okay, it's more useful to have that than red philosophy, but I will now show you what the answer is in terms of red philosophy. Okay, so if we're going to add all of these monomials together and we want to get the final polynomial, want to get the final symbol that it's actually going to equal in our ring of polynomials, how do we actually do that? Okay, well, what we need to do is we need to collect together all the same powers of x, okay, and we need to add together all of the coefficients that they've all got in front of them in the commutative ring, because remember, that's the way that we add monomials together, or indeed it's the way we add polynomials together. We add the homologous or equivalent coefficients that are in front of the same power of x, so we add component-wise. Okay, so we just need to collect together all of the coefficients that are in front of equivalent powers of x. Okay, so writing this out, let's now go the sum over n, okay, so just using a new index, and then we'll have xn here, and now what's the coefficient going to be in front of each xn? Well, for each n, there are loads of possible combinations of I and j that would give that n. Okay, so we now need to acknowledge that. So what we'll want is the sum from I is equal to 0 to n, and then I'll want everything of the form ai, and then I want bn minus I, and I hope that makes sense, because what I want is I plus j to equal n. Okay, so I want all combinations of I and j such that I plus j is equal to n. So if I let I vary from 0 to n, then I've just set j equal to the other portion, basically, that it would need to be in order for them to add together to give n, okay, which is n minus I. So n minus I here is effectively my j, but I've curtailed it because I want I plus j to equal n. So if I is the value between 0 and n, whatever value it is, then j is going to have to be n minus I. Okay, so all that involves doing basically is summing together all of the coefficients in front of the same monomials in this great big sum. And you'll be doing that sum in the ring, so I might just underline that in red. This sum is all done in the ring, so we're multiplying these two elements together in our original commutative ring R, and then we're adding them all together in the original commutative ring R to get one final coefficient here that will be in front of each power x to the n. Okay, and this now is the final symbol. Okay, that is the actual answer. That's the final polynomial answer to what this polynomial multiplied by this polynomial is. Okay, however, as I say, it's more useful to think of it in terms of turquoise interpretation here as being the sum of all of these monomials, and then you can worry about actually having to sum up those monomials and collect the coefficients together later on. Okay, that form is more useful for actually proving the properties that we will want to prove in a moment. Okay, right, so that's how we're going to define multiplication of two polynomials. So now what we need to make sure of is that this multiplication law does indeed actually obey the axioms that we need it to obey in order for the ring of polynomials to actually become a ring. Okay, so there were 5 axioms that we need it to obey because we want it also to be a commutative ring. So we'll start off with axiom number 1. So axiom number 1 is closure. Okay, and that says that the answer must be another element of the ring of polynomials. Okay, so why is that always going to be true? Well, certainly all of the coefficients that we're going to get in front of the monomials here are going to be elements of the ring, so it's looking hopeful, but we also need to make sure that the final thing that we do end up with is going to have only a finite number of coefficients not being equal to 0. Okay, and the reason that's going to be true is this has a finite number of things that are not equal to 0. This also has a finite number of coefficients that are not equal to 0. The maximum possible number of terms then that you would get here that would not have coefficients equal to 0 is just the number here multiplied by the number here. Okay, and then of course you have to gather together terms which have the same monomial, so overall it will most likely end up smaller than that. So the final thing that you end up with is going to have a finite number of non-zero coefficients. It can't not have if these two things both had a finite number of non-zero coefficients. So closure is fine. We will end up with another polynomial in our ring of polynomials. Okay. Axiom number 2, multiplicative associativity. Now this is where it's best to use this turquoise interpretation rather than the red interpretation here. Okay, it's best to think of the answer as being this sum of all of these monomials where you're summing them up in the ring of polynomials addition law. Okay, you could perform that sum and finally get the answer in terms of the actual symbol, but it's going to be more convenient for us to work in this sort of bit that's prior to the actual end answer. Okay, so axiom number 2 then, associativity. So what we want to show is that if you multiply 3 polynomials together, it doesn't matter where you put the brackets. Okay, so let me write this out explicitly. So if we have the sum over I of ai xi multiplied with the sum over j of bj xj multiplied by the sum over k, let's say, of ck xk like so. So here are 3 polynomials, and at the moment you can think of them as actually being in their symbol form. I think of these sums as just the arbitrary symbols. Okay, now what we want to prove is that it does not matter where you put the brackets. So you can either put the bracket for the multiplication around these two, or you can put the multiplication bracket for the multiplication around these two multiplied together. And we want to prove that the overall answer that you will get is exactly the same. Okay, so how are we going to do this? Well, we're just going to do both ways and prove that the answer is going to be exactly the same. So let's start off with the purple way. Okay, so firstly then we want to multiply polynomial A here with polynomial B. So the first thing we'll do is move from viewing this polynomial as the abstract symbol to now viewing it as the sum of the monomials, where the sums are carried out in our actual ring of polynomials. Okay, and because the turquoise pen is running out, I will underline it in orange rather than turquoise. Okay, and then we'll do the same thing for our B polynomial here. So again, we'll view it as just this sum of monomials where the addition is now carried out in the ring of polynomials. Then what we can do is apply this formula here, okay, which has to be true if we want the multiplication to have any chance of obeying distributivity. Okay, so it will become the sum over I, the sum over j of ai times bj, where that multiplication is carried out in the original commutative ring R, and then we add the powers xi plus j like that. Okay, so you'll need to sum up all of these monomials in the addition law that's on our ring of polynomials to actually get the end answer. Okay, so this isn't the final answer, this isn't the final abstract symbol answer, but you can use this to actually end up with the final abstract symbol answer just by adding together all of these monomials in the ring of polynomials. Okay, then what we want to do is take this and we want to multiply that with this thing here. So we want to multiply that with the C polynomial here, ck xk, like so. So again, the first thing we'll do is we'll move to viewing this as a sum of the monomials rather than in the abstract symbol sense. So we've got a great big sum of monomials here multiplied with another great big sum of monomials. Again, we can just apply distributivity and the way that we defined multiplication of monomials to end up with the fact that this will just equal the sum over I, the sum over j, the sum over k, and then we'll have ai bj multiplied then with ck, and then that will be the coefficient in front of x to the power of I plus j plus k, like so. And of course we know that addition obeys associativity, so I won't even bother putting the brackets there. Okay, right, so here then, this final thing that we've got here, this is just a great big sum of monomials. So again, it's not the final answer, so I'm sorry that I've underlined it in red, but forget the colour coding now. This is not the final answer. This is a sum of monomials. This is something that you could actually perform. You could work out what all of these monomials added together actually is in the ring of polynomials, and then you would get the final answer. Okay, so you can go from this to get the final answer. Okay, right. Now what I'm going to do is I'm going to consider what we'd get if we did it the green way. And I'm going to show you that we'd again get a great big sum of monomials like this, and that all of the coefficients in front of all the monomials would be exactly the same, and therefore that the sum of those monomials must end up actually giving you the same final answer. Okay, so green way then. Okay, so if we firstly multiply bj x, well, the b polynomial here with the c polynomial here, of course that will give us the sum from over j, the sum over k, bj ck, x j plus k, like so. So again, this is a great big sum of monomials, which if you actually did perform that sum in the ring of polynomials, you would end up with the abstract polynomial symbol, which is the answer to this. Okay, then what you're going to do is multiply this great big sum of monomials with this sum of monomials. You're going to take this sum of monomials and multiply it with that one. Okay, and again, the final answer, what you'll get is the sum over I, the sum over j, the sum over k, and then you'll get, this time, ai bj ck xi plus j plus k. Okay, so again, this is a great big sum involving loads of monomials being summed together using the addition rule that we have now defined on our ring of polynomials. Okay, and hopefully you can agree that even though we haven't actually got the final end abstract symbol in our polynomial ring, these two sums, if we performed both of those in the ring of polynomials, we would end up with the same answer. Why? Because all of the monomials are exactly the same that we're adding together here. Because this coefficient here will always equal this coefficient here, no matter what I, j, and k you are working with. Okay, so all of the coefficients in front of all of these monomials are going to be identical, so you're actually performing the exact same sum of monomials. And the reason those two are going to be identical is, of course, because multiplication is associative in our commutative ring R. Okay, so that's then how you can prove associativity using associativity of the original commutative ring that we started off with. And as you can see, it works quite nicely if you use this interpretation here, i.e. you don't actually have the answer, you have a sum of monomials that you could use to get the final answer. If you use this, you can do it. I mean, it's not impossible, but it's incredibly confusing and difficult. Okay, so if you use the actual answer here, it does become quite difficult. Okay, so we haven't finished yet, but we'll have a break here and we'll finish the final 3 axioms that we need to prove in the next video.